Good. Okay, so we'll just take a couple of minutes revising what we have done in the last class, and then go to rate matching and other things today. Okay, we'll start understanding HARC and rate matching a little bit today. Okay, we'll quickly go through. Excuse me. Excuse me. Just 1 minute. Sorry. Okay, we'll quickly go through what we have done last class, and then for 5 minutes, and then go ahead with the next new one. Okay. So what we learned was PDUs come from MAC layer in terms of something called transport blocks. And for 4 layers, you have up to 4 layers, you have 1 transport block. More than 4 layers, you'll have 2 transport blocks. Okay. And transport block is always a UV based transport block. So every transport block goes to 1 UV. Okay. The first thing that happens is, depending upon the length of the transport block, which is denoted by size A, you either add a 24-bit CRC or a 16-bit CRC. Okay, so at the output of this CRC, you have A plus L is the length of the whole system. Then you also choose your base graph. So you, based on scheduling and other things, you have a rate that comes, R rate that you want to support. And you also know your code block size, transport block size A. So based on this, you choose base graph 1 or base graph 2 from LDPC. Okay. So base graph 1 corresponds to a larger input frame, block width, whereas base graph 2 corresponds to a smaller block width. Okay. So at this point, you can select the base graph just by looking at A and R rate that you want to achieve. And then what you do is, if your input transport block is larger than the maximum code block size for that particular base graph you have chosen, you break your transport block into multiple code blocks. Okay, and for each code block, you add on a CRC, a 24-bit CRC. Okay, any questions till now? Okay. Okay, so the number of code blocks is denoted by C and is given by ceiling of the total number of bits B. Remember, B was A plus L divided by, A plus 24 or 16 of the TBCRC divided by KCB minus L. L here is 24. Okay. So after this, so essentially B dash will represent the total number of bits, in this code block. All the code blocks combined with their CRCs is denoted by B dash. Okay. So now you want to, so K dash is nothing but B dash by total number of code blocks. Okay. So, and then based on the particular choice, you choose for the base graph, you choose something called KB. And from the KB, you find a lifting factor so that this is greater than K dash. And finally, you set your block length to be equal to 22 times Z. 22 times Z for BG1 and 10Z for BG2. Okay. So summarizing this, so you have a transport block. Okay, the transport block with CRC size of L. So essentially, it has K plus L. Okay. So.
Sir, excuse me, sir. Sir, for BG2, the KB will be always 10G, or because in the previous slide it was sometimes depending upon the B size, the KB also have KB, smaller size like 6.
Yeah, KB changes, but KR is always 10Z. Okay, KB is used to just find out the lifting size, such that the KB into lifting size is greater than K dash. Okay, so remember, see that this KR will always be greater than KB. KR is always greater than KB for base graph 2. So if your KB into Z is greater than K dash, 10 into Z will also be greater than K dash. Does it make sense, Sitanjan? So essentially, you want to cover this whole K dash bits input. Okay. So yes, finally, 10Z is the input size and 22Z is for BG1. So you see that 22 is always greater than KB for greater than or equal to KB for base graph 1, and 10 is greater than or equal to KB for base graph 2. Okay. So finally, KR is the number of input bits that you feed into the LDPC encoder. Okay. So the difference between K dash and KR, you fill it using filler bits. That's what I'm showing here. Okay. So this is up to K dash. Okay. So essentially K is equal to KR. K is the same for all the code blocks, so it's called K. Okay, K minus K dash filler bits to fill. So this whole thing will be the input to your LDPC encoder. Okay, so if you come back here, let us understand it. So you have K bits. Output of code block segmentation will be K bits. Yes, K bits correspond to what? K bits corresponds to K dash information bits and K minus K dash null bits. Yes, filler bits. So these filler bits, before you feed it to the LDPC code, are changed to zeros. Okay, how many zeros are there? K minus K dash. Okay, so the total number of bits that go into LDPC code is K, which is nothing but 22Z for BG1 and 10Z for BG2. Okay, is this clear? You understood this part? Okay, so then what happens? Then you have an LDPC code. LDPC code for the BG1, now I'm using BG1, will produce 68Z bits. You give it 22Z bits, it will produce 68Z bits. Out of that, what you do is, for the first 2Z bits, you puncture them. Puncture them means you just drop them out. Okay, so how many are left? 66Z bits are left. Okay, so the 66Z bits are what you effectively transmit. In this also the null bits also will be lost. So the effective code rate of after puncturing is 1/3, because you input 22Z bits and output you get 66Z bits. So 66Z by 22Z is 1/3. Does it make sense? Any questions here? Okay. Similarly for BG2, you have, you do 50Z bits come out. 52Z bits come out of the LDPC code. 2Z bits you drop, so you get 50Z bits out. So input is 10Z for the LDPC code. The effective output is 50Z. So effective code rate for BG2 is 1/5. Fine? Does it make sense? So at this point, effectively you have a code rate of 1/5 for this and 1/3 for this, for BG1. Okay. So we have to understand how do you increase the code rate or how do you decrease the code rate, because you can't just transmit only 1/3 code rate or 1/5 code rate. So any questions before I proceed?
Sir, here the input and output of LDPC code is one-dimensional array or?
It's a one-dimensional bit stream.
Just bits.
Yeah, it's just bits. Okay. So the effective LDPC code, how you choose the base graph values and other things, I'm not talking today. That day I talked. So you guys have a look at it once. It will become clear. Okay. So today we'll go to the next topic, which is called the rate matching. Okay. So let's understand this problem of rate matching and other things cleanly, and see what we, how do we achieve this rate matching? What does it do and other things? Let's understand this part clearly. Okay. Okay. So what is the purpose of rate matching? Okay. So now that the output of FEC, you always have, see, at this point, you always have 66Z bits for FR1. Sorry, 66Z bits for FR. 66Z bits for BG1 and 50Z bits for BG2. Okay. The question is, how do you make sure? So this is a problem that we saw that day. How do you make sure that the output of FEC, after FEC, what is the next block? Generally, high level block that you have, you will have the modulation block. Okay. So these FEC bits are taken and mapped into constellation points. Okay. So these constellation points have to fit in the RE grid that you have. The question is, how do you do that? And how do you achieve whatever code rate you want effectively? Okay. So remember, our effective code rate is given by R. This is approximately the code rate that you want. Okay. This is given by scheduler. Okay. You say that the effective code rate is 0.67. So this is the effective code rate you want. But at this point, what you have is, you have 1/3 and 1/5. Okay. So how do you change your code rate? Okay, so that's what we have to understand. Okay, so I'll just share my screen and let me just write up something. So you have the resource grid. In this, every user is allocated some resource elements, some number of REs. Some number of REs is allocated. Okay. So in this, what are the issues? The issues are that there are some things which are pilots. That's one issue. And the second thing is, each of this will be filled by some kind of modulation, some constant modulation. In the sense that it can be 4 QAM in QPSK, 16 QAM, or 64 QAM, or 256 QAM. Okay, so you should fill this. Okay. Okay. So if the number of, so essentially effectively what this means is the number of effective bits, if QM is your modulation order, QM is your modulation order. Okay? QM means approximately, QM tells you the number of bits per symbol. Okay? For QPSK, QM will be 2, 16 QAM it's 4, 64 QAM 6, and 256 QAM it's 8. Okay? So the number of bits that you have should be a multiple of QM. Is this clear? Yes. So if you have 4 RE and you are using QPSK, how many bits will you do? You will do 8 bits. If you are using 16 QAM, it will be 16 bits. If you are using 64 QAM, it will be 24 bits. Okay. So the number of bits that come out that you finally require should be a multiple of QM. Otherwise, you cannot fill the grid. Is this clear? Any question here? Okay. Again, the number of bits should fill in. When I say fill in, it means after you modulate, after you put in the modulation, should fill in all the allocated RE except for the pilots in the grid. Okay, so if this whole thing is allocated to you, what you have to do is you have to subtract off the pilots and other things, and then you find the effective number of RE that you have, that you can actually use for information. Okay, and that into number of QM should be the effective number of bits that you have. Is this clear? Any question? Okay. Okay. So this should all happen. Okay. So now let's get back to the slides. Okay. Oh, sorry. So there's one more thing. If you have multiple layers, which is MIMO, multiple layers means you'll have multiple resource grids. Each resource grid goes into one antenna. Okay. So the number of bits should also be a multiple of number of layers. Okay. So if there are 3 antennas, if there are 4 antenna, you want to transmit on 4 antennas, you have to fill 4 resource grid. Now each resource grid goes into each antenna. So the number of bits should also be a multiple of layers. So your resource grid should be a multiple of layers. It should be a multiple of QM, and the number of bits should fill in exactly into the number of resource elements you have after modulation. Okay. Okay.
May I ask one question?
Yes, sir. Please.
Yeah. In case an UE using say 2 or 3 bandwidth part, and every bandwidth part is a different numerology, that means it will have 3 grids. I mean 3 grids. If there is a 3 bandwidth part with different numerology, then there will be 3 grids, right?
No, sir. See, for the bandwidth part, it will be the same grid, but different frequency time locations. Okay. But if you have layers, the grid will be different.
Okay. So my example is, suppose I have 2 bandwidth part which I am using as a UE, and
sure. I will tell you this. Okay.
And in every bandwidth part, if numerology is different, so whether
if numerology is different, numerology is different. Yes, what you say is true. Effectively, you will have different grids.
So that can we call that it's a 2-layer transmission?
No, sir. Layers by definition, layers are only at different antennas.
Okay, if antenna is different, then that's a layer, right?
That's a layer. That's a layer. Yeah.
In case of a bandwidth part, same antenna would be used.
Same antenna will be used. I mean, depends on those bandwidth parts are transmitting different antennas. I mean, all those issues there. But layer generally means different antenna. So this may be BP. I mean, sorry. This may be bandwidth part 1. This may be bandwidth part 2. But then the same grid.
Okay. Okay. Within the same grid, also there could be multiple bandwidth part, and it could be separate also. So when we say layer, it is always more than one antenna. The transmission is happening. So two antenna means different frequency band we are trying to transmit. Is it that is that a carrier aggregation or what?
So see, I mean, what you generally when you do layers, you transmit in the same frequency band. Otherwise, it doesn't make sense now. Why it was? I mean, you can also do that. There's nothing that prevents you. Carrier aggregation is completely different, sir. Carrier aggregation means essentially you have two different carriers itself. Okay. So
the multiple layers means what? I mean, I'm sending separate data on each layer.
You can do that. You can send separate data on each layer. You'll have a pre-coder. I'll come to that, sir. In the next class, we'll start the MIMO. It will become very clear about that. Yeah.
Okay.
So once we finish this part, the bit processing will be done. Then the next step is a pre-coder. That's where MIMO I'll introduce what is ports, what are layers, other things.
Okay, fine.
Okay. So for now, for this class, what we'll assume is number of layers. Just to think about it, we can assume that each layer corresponds to different resource grid, and that will be going to different antennas. Okay. Okay. So G is the total number. So once you know your resource grid, and you subtract out all the pilots that you have to put, you will know effectively number of resource elements that you can use, and you also know the modulation order and the number of layers. So based on that, you can calculate the total number of bits that can fit in the arrays, that are allocated to the particular user. Okay, so these are the arrays that you have. These are the actual physical arrays that you have. Okay, from that array, you can compute the total number of bits by multiplying with QM and number of layers so that you get G. So G is the total number of bits you can fit in your allocation across layers and across different arrays. Okay. So now the first challenge would be you have certain code words. Okay. So now what you have G. Okay. So for example, G can be 30,000 bits. I'm just giving an example. Okay. So now what you should do, whatever is coming out of your LDPC, you are getting code words that you have to fit in this 30,000 things. Okay, in this 30,000, how do we do that? Okay, the one way of thinking about this is if you divide G into C number of code words, then what you get is G by C. Okay, so the problem is G by C need not be an integer. Okay, so how do you tackle this? Okay, so let me take an example. I'll explain you this how people tackle this. So you have 10 bits. Okay, 10 bits you want to divide into 3 parts. Okay, you have 3 code words. I'm just giving an example. This is an example. Okay, this is too small number. How do you divide 10 into 3 parts? Okay, of course, 10 by 3 is not an integer. It's not an integer. You cannot divide a bit, na? So one thing you can do is 3, 3, 4. This is one way. Okay. So how do you get 3, 3, 4? This is nothing but 3 by 3 is nothing but 10 by 3 floor of this. Okay, so this is called the floor operator. X is the floor operator. Okay. What is the floor operator? So 2.5 if I give, the floor of 2.5 is 2. You just drop the decimal place. Floor of 3.1 is 3. Okay. Similarly, there's a ceiling operator. Seal operator. Seal of 3.1 is 4. Seal of 2.5 is 3. You understood? So ceiling means you round off to the greater integer. Floor means you round off to the smaller integer. Agreed? Okay. So this can be written as 10 by 3 floor, 10 by 3 and seal of 10 by 3. Okay. 10 by 3 is 3.333. So floor of 3.33 is equal to 3. Again, this is also 3. Seal of 10 by 3, seal of 3.33, which is equal to 4. Is that fine? So I can write this 10 by 3 plus 10 by 3 plus seal of 10 by 3 will be equal to 10. This is a proper equation. Okay, this is true. Of course, this is not, these are not true. 10 by 3 into 3 is not equal to 10. Okay, similarly, 3 into seal of 10 by 3 is also not equal to 10. Okay, these are wrong. Okay, so if you want 10, what you should do is some of them should be floor and some of them should be seal. Okay, so that's how you divide them into roughly equal. I mean, some of them will not be equal, but most of them will be equal. Okay, just to summarize this properly in a mathematical form. So what do you want? Okay. You have G bits. Your modulation order is QM. Your number of layers is L, and number of code blocks is equal to what do you say is C. Okay. Now I want to divide this G bit so that C code blocks, whatever code block comes, the total should be divisible by QM into L. Okay, and the total, I mean, then you should have C code blocks. How do we do that? Okay, so that is what I'm going to show you now. Okay, so roughly each code block should contain how many bits? It will be G by C into this one. Why should this be the case? So each code block should be divisible by number of layers and divisible by QM. That's why divided by Ni, number of layers into QM, and multiplied by NL into QM. Okay, approximately G by C into NL into QM will be the. Okay, so G by C will be the approximate length of a code block. Okay, because we want C code blocks. But I'm just making sure that the G by C will not, need not be a multiple of number of layers and number of modulation. So I'm dividing by that and multiplying by that and taking a seal operator. Okay, but the problem is, as I told you before, C of these will not be equal to G. They should also add up to G, now total number of bits. So what we do is we take few seals and few floors. Okay, so this is the example I gave. 3 into seal of 10 by 3 is not equal to 10. So what you should do, you require 2 floors and 1 seal. How many floors you require? You require 3 minus the denominator minus mod of numerator and denominator floors, and 1 and these number of ceilings you require. Okay, so that's how they divide the bits across the code blocks. Okay, so what they do is, you require G bits. Okay, so what are the constraints? Length of each code block should be a multiple of QM and L. Okay, and there should be C code blocks. Okay, and the sum of the total number of bits in C code blocks should be G. Okay, so the first thing that you should understand is G by C. I mean, if everything is a multiple, G by C would suffice, but this is not a, I mean, this need not be a multiple, this is not be an integer also. So you take a seal. You also divide by number of layers. Okay, I mean, number of layers NL and QM, and multiply by NL into QM. Okay, so if you take this as the size of the code block, this as the size of your code block, this automatically will result by NL and QM, both NL and QM. But what is the problem? This into C need not be equal to G. Okay, because that's the total number of bits you have, total number of bits that you can fit in your grid. Okay, so what you do is some of them will have seals and some of them will have floors. Okay. Okay, so how many seals will be there? How many? First, let's do the how many floors. How many floors will be there? It will be C minus mod of G divided by NL into QM, comma C. And seal will be, number of seals will be mod of G by NL into QM mod C. Okay. So this is exactly like how I said 10. So you have 10 bits. You have to divide into 3 parts. So essentially 10, you'll have 10 by 3 plus 10 by 3 plus 10 by 3. Okay. How many ceilings are there? That is mod of 10 comma 3. Mod of 10 comma 3 is remainder of 10 when you divide by 3, which is 1. Okay, so one seal will be there. 3 minus that will be the number of floors. This is 2, this is number of 1. Okay, so that's how you divide the bits across different code blocks. Okay, so some of the code blocks, the effective length. Okay, so now we know how to compute the effective length of each code block. Okay, some of the code blocks length is NL into QM into floor of G divided by NL QM into C. Okay, sum of the code block length is NL QM into ceiling of G divided by NL QM into C. Okay, so the total number of this I have given here. This is the number of floors and this is the number of ceilings. Okay, okay. So now we have decided the code block lengths, effective code block length that you should have. Okay, so let's call the code block lengths as what do they call? Let me just see 1 minute. Okay, so ER, so R is equal to 0, 1, 2, C minus 1 is the effective code block length. Okay, do you understand this? What is the effective code block length? So this ER will be the floor and these things. I mean, for some things it will be like this, for some things like this. Okay, there are C code blocks. So it's effective code block length. Okay, this is what we have. This is what we have computed. Now, what is coming out of your LDPC? Out of your LDPC, how many bits are you getting? You are getting totally. Let's see how many bits were we getting out of LDPC. For each code block, you are getting, after puncturing, how many are you getting? 66Z for BG1, 50Z for BG2 for all the code blocks. Yes? Okay. So now what we should do is, ER and 66Z may not be equal. Similarly, I mean, let's just focus on BG1 so that it's easy for us. Okay. So you have some code blocks and you want those lengths to be this, but this is the length that is coming out of your LDPC encoder after you do puncturing. Okay. So how do you match ER to 66Z? How do you make sure that this effectively gets matched? So this is where rate matching comes into picture. Okay. So one thing that you should remember is in the 66Z bits, some of them are filler bits. Okay. So how many filler bits did we put? We put K minus K dash filler bits. Remember, null bits are filler bits. Okay. Just let me show you the slide one so that you can recall. So remember this 0000 that we have introduced. These filler bits have been replaced by 000, and there are K minus K dash such bits. And these bits are useless bits because they have no information. You don't want to transmit them. Okay, you don't want to transmit them. So how do you now match this is the question. Okay, so this is where what is called rate match. So what you do is you take a circular buffer. This is done for each code word. Okay, you take a circular buffer. Okay, I'll tell you the length of circular buffer and other things later. What you do is you write your code word. So the output of LDPC is 66Z bits. I'm just going to focus on BG1. Okay, so you write B0, B1, B2, so on. Okay, something will be there. Then you'll have some filler bits. Again, the bits will start. How many bits will be there like this? I'll tell you the exact numbers in the slides. B66Z minus 1. It started B0. Okay. Then what you do is, this is what you got as output of your LDPC encoder. Yes, LDPC encoder. So the first code block you want E1 bits. Okay, the second code block is E2 bits. Let's just focus on the first code block. Okay. What you do is you start at this point. Okay. So this is, and you just count E1 bits, excluding null bits. Okay. So excluding null bits, you count even bits. Okay. Sometimes what might happen if your code rate is very low, you might have to do one more circle. You might have to come like this. On the other hand, if your code rate is very high, you may not even use all the bits. You might have to stop at this point. Okay. So this is called as rate matching. So you get a fixed output from your LDPC, but what you have to fill in the grid. Okay, the grid size also depends on your rate. Now, when you choose your rate itself, you choose this is the amount of data I have, this is the rate I have, so I'll choose a bigger grid. Okay. So the amount of data that you fill, how do you take from the fixed block length? You put in a circular buffer and then go around. If you require more, or you stop at some point if you want smaller number of bits, so that you get exactly even bits. You do the same thing for the second code block. You fill in those bits and you get for E2 bits. Okay, so on and so forth you do. So that exactly when you add all this, you get G bits. Is this clear? Okay, I'm going to show you in this, where I put all the numbers and other things.
The G bit should not include null bits, sir.
GB will not have null bits. We will not transmit because they do not have any information. So we exclude when we are transmitting. So when we are going around the circular buffer, you don't count these null bits. Okay, you start at this position. You take ER bits, but excluding the null bits.
How it differentiates, sir? Because normal bits also can be zeros, and these null bits.
Yeah. But you know at which locations they are, the transmitter. See, Vijay. So you know exactly the locations. If you look at this part, you know exactly the locations. After K dash, from 2Z to K dash is data, because you first drop the first 2Z bits. Then it is followed by K minus K dash null bits. You know exactly those numbers.
Okay.
So you just drop them. Okay. So effectively what happens when your code rate is high, you are not transmitting all the parity bits. Okay, so the number of parity bits you transmit will be low. Okay. On the other hand, when your code rate is low, what happens is your LDPC is giving only code rate of 1/3 for at least BG1. Then what might happen if you want 1/4 code rate? I'm just giving an example, 1/4 code rate. Then what you do is you go around the circle one more time. You might have to go a little bit here. So you transmit more, you are transmitting more number of parity bits and more number of the same data bits again you are transmitting. Okay. So effectively your code rate will increase or decrease based on this rate matching. That is one thing that you should tell. I didn't tell you about what is redundancy version. I'll tell you in a minute. Is this clear? What you do, what is meant by rate matching and circular buffer? So effectively the output, your LDPC encoder is fixed code rate. Okay. But what you want to fill in each code block in the grid may have different lengths. Okay. So what you do is you use your circular buffer and then start reading from the top, and either you go circular or you don't finish the circle depending upon your code rate, effective code rate. Yes? Does it make sense? Okay. So there's something called redundancy version 0, redundancy version 1, 2, and 3. Okay, so what is meant by redundancy version is, so this comes in half. Okay. So first time you transmit, this is the first time fresh bits you are transmitting to the UE, or is the other way around also. You always start at RV0. RV0 is the beginning of the code block. When you write in the circular buffer, there's a D0. Okay. You transmit some number of bits after you exclude the null bits. Suppose this transmission failed for whatever reason. This transmission failed. Then you get a negative acknowledgement. Then you have to retransmit. When you retransmit, there are multiple ways of doing retransmission. One is called as incremental redundancy, and the other is called as, I forget the name of the term. You transmit the same thing. I don't forget the name, technical name for that, I'll tell you. Where you transmit the same bits again. Okay. So what we use is, we use something called incremental redundancy. What you do is, next time you don't transmit the same bits again. You don't start at RV0. You count the bits from RV is equal to 1. Okay, so this RV, what is meant by RV is defined in the spec. Okay, where does the start point for each RV starts is defined in the spec. I put the table here. Okay, it depends on your lifting factor and other things. Okay, so next time you start at this point and count those many bits and go. Okay, so effectively what you get is, you get different set of parity bits now. Even now, if it fails, you start RV equal to 2, you start at this point and go circle from there. If that is also failed, you go to RV3 and you give from this point. Okay, even if this fails, then you decrease your code rate. Effectively, you decrease your code rate or your modulation and transmit at a much lower rate. Okay, that at that point at RV equal to 3, the UE will say, I can't decode anything. Your channel is very bad, so you have to do something else. Okay, so this is called the redundancy version. Redundancy version 0, redundancy version 1, 2, 3. Okay, so effectively those indicate the position in the circular buffer where you start taking your bits from.
Is this some kind of memory, sir? Memory storage?
Sorry?
Is this some kind of memory storage, sir? It will be stored.
It's a memory storage. So essentially what happens is, I mean, it depends on how your implementation is. You have to store this, I mean, effectively you have to store these data bits in the transmitter till you get an acknowledgement, effectively. Yeah, how they implement, that's a complicated thing. I mean, sometimes people may recompute everything. Sometimes people may store them and in the circular buffer and keep the circular buffer, and only once they get an acknowledgement, then they flush the circular buffer. Okay. Otherwise, they'll use the same circular buffer once to transmit RV0, next to transmit RV1, 2 and 3, depending upon the ACK or NAC. Vijay, does that answer your question?
Yeah, yes, sir.
Okay. I mean, how they implement it is, I mean, it's a little bit more complicated. Okay. Any questions? Okay. So the starting positions for the different redundancy versions is given by the table. Okay. I mean, you can compute that. Okay. So the transmitter and the receiver, both of them know where the second set of bits are coming from, which part of the circular buffer they are coming from, the locations at least. Okay. So this is what I told you. At lower rates, what might happen is you might have to go along around the circle one more time. Okay, for higher rate, you will transmit a fewer number than bits that are there in the circular buffer. You may not even finish the circle even once. Okay. So this is kind of an important thing. I mean, this is a little bit more technical. I just want to emphasize, I mean, I want you to understand this a little bit. Okay. The output of LDPC code, actual LDPC, was 68Z. Okay. Out of that, what did we do? We dropped the first 2 Z bits beginning itself. Okay. Then in the rate matching, you may drop these other parity bits depending upon what is the rate. Okay, this is called puncturing. Here, what did you do? You also introduce filler bits. Okay, so when the filler bits, before they are entering into the LDPC encoder, you replace them with zeros. Okay, this is called shortening. Okay, why is it called shortening? You use those filler bits to encode, but you do not transmit them. You shorten. You are not transmitting the filler bits. Those null bits you are not transmitting. But when encoding, you put them as zeros. Okay, that is called shortening. Puncturing means dropping off. Shortening means you put some filler bits, you use that to encode, but then you finally don't transmit them. Is this clear? Okay. The receiver, what do they do? The receiver, the filler bits will be again filled by 0 before they send it to the decoder. Okay. The punctured, so essentially, I mean, I'm talking in terms of LLR. So LLR, I mean, don't worry about it. So essentially the punctured bit, so effectively what they do with the puncturing bits is, they assume that these bits can be 0 or 1 with probability half. Okay. So there's one small thing I'm going to take 5 minutes and explain you how the decoder works. What is a modern decoder? What is meant by LLR? Okay. So you look at the encoder. Encoder, what does it do? Encoder takes in bits, and gives you bits. Okay. So it takes k bits and gives you n bits. Okay. Then what you do, you transmit this on the channel, and you receive the bits, and you receive your constellation points. And from the constellation points, what did you do? You try to decode bits. You pass it through your decoder. Okay, you pass it through your decoder and you get your bits. This is FEC decoder. Okay. So there are 2 types of decoders. One is called the soft decoder. Another is called the hard decoder. Okay. So what is meant by first hard decoder? What is meant by hard decoder? Hard decoder means you do your channel estimation, you do your equalization and other things. After this, after you get your constellation points, you demodulate them. You demodulate them into bits. Okay. And then pass it through your decoder. Okay? This is called a hard decoder. Yeah, this is very straightforward. So your decoder works. Decoder input is also bits. The output is also bits. Exactly inverse of your what is there in your encoder. Okay, this was called the hard decoder. So this hard decoding was used in up to 70s or 80s. I mean, maybe in the 80s also it was quite popular. Hard decoding was used. Okay. So the decoder also works on input is bits and output is bits. Okay. Okay. But then they came up with this new technique called soft decoding. What is soft decoding? Okay. The main idea of soft decoding is that all bits are not equally reliable. Okay, what does it mean? What does the statement mean? Let's just take BPSK. Okay, let's just take BPSK, where you map 0 to -1 and 1 to 1. This is bits, this is values. Okay, you understand that? No? These are bits, these are constellation points. Okay, so if you look at the constellation point, you'll have 1, you'll have -1. Fine? Okay. So now what happens? You transmitted something. So suppose I transmitted 1. This is what I transmitted. I transmitted 1. What happens? Noise gets added. Okay. When noise gets added, noise is a Gaussian process. Okay, let's assume it's a Gaussian process. So what will happen? Effectively, this is the probability distribution of what you receive. In the sense that most probably you will be around 1, but there's a lower chance that you can go very, very high to plus infinity. Similarly, there's a very, very small chance that you can go this way also, minus infinity. Okay, this is the probability distribution of that. Okay. So what will you receive? You'll receive a real number. At the receiver, you'll receive a real number. Maybe you receive 0.76. Yeah, you received 0.76. This is the value you received the receiver. So y is equal to x plus noise is equal to 0.76. Okay. So suppose I tell it's 0.76. How will you decode it? What will you decode it to?
Towards 1, sir.
You will decode it to 1. Okay. So this, when you do a decoding, you will get 1. Okay. Okay. Next, what happens? Suppose you get y is equal to, next time you transfer the same one, you get 0.01. Okay. When you decode this, what do you get? Hard decoding. When you decode this, what do you get?
1.
Again, you get 1. Okay. But now let's think about this. You are more confident that 0.76 would correspond to 1 here because it's very close to 1. Okay. 0.76 will be somewhere here. Okay. On the other hand, 0.01 is very, very close to 0. Okay. So it's very intuitive that 0.01, while might be 1, but it's not with so high probability compared to 0.76. Yes. Okay. So if I tell you it's 0.76, you have much more confidence. You can tell 0.76 equal to 1. Whereas if I tell 0.01, that what you received is 0.01, your confidence level goes down. Does it make sense?
Yes.
Yes. Okay. So there's a higher chance that there's a chance that this 0.01 could have also been -1, which has just moved on the other side. Okay. So the values that come close to 0, your confidence is low, whereas the values that are away from 0, your confidence is high. Yes. But when you decode like this, when you hard decode it, both of them show 1. At that point, you lose this confidence. Okay, this is called what your confidence about that bit. Okay, so this is called as soft decoding. So in the soft decoding, what you do is you don't pass ones or -1s. You pass these real numbers that you get. Okay, so these real numbers are in some sense proportional to the probability that it's most probably a 1 or 0, 1 or -1. It's proportional. Okay. So these are called as log likelihood ratios. Okay. So for every bit, you compute logarithm of what is the probability. It's a 1 given whatever you have observed. By probability, it's a 0 given whatever you have observed. Okay. So if this is called the LLR for that bit. Okay. You can immediately see if that LLR is greater than 0, it implies your bit is 1. On the other hand, if it's less than 0, it is bit is 0. Okay. So effectively, what you are doing is all your modern decoders can take these values rather than this hard decoded bits. Okay. They'll take these values and do some probability distributions. They'll understand, okay, suppose, okay, I'll give you a very, very simple example. Actually, this is a very simple example we can give. Okay. Let us do this. Okay. Let us do repetition coding. So what is repetition coding means? Repetition coding means every bit I repeat it 3 times. I'm just repetition coding 3. Okay, I'll repeat it every 3 times and transmit it. Okay, and the receiver, what do? How do you decode it? You see the, some of these bits can get flipped. Okay, maybe this you got 1 1 0. What do you decode this bit? This is your error control code. Now, what do you decode this as? You'll decode this as
1, sir.
You decode this as 1 because majority times you got 1. Okay, similarly, 0 also you transmit it 3 times. If you get 0 0 1, you will decode it 0. But on the other hand, if you get 0 1 1, you decode it as 1, which is an error. This is called repetition coding. Okay. So now let's pass it through an AWS Gen channel, and I'll tell you. So you transmitted 1, you got these values. First time you got 1.3, Second time you got minus 0.1. Third time you get minus 0.01. Okay. So let's do hard decoding. Okay, so this is y is equal to x plus n. So if you do hard decoding, 1.3 will be hard decode to what? It will decode to the bit 1. This will be decoded to bit 0. This will be decoded to bit 0. So what will you declare output as? What will you declare your output as? Because you got
0,
you will decode the output.
0.
Okay. But if you do soft decoding, what I do in soft decoding in this particular case is I add all the received values. Okay. So I'll get 1.3 plus minus 0.1 minus 0.01, which will be how much? Which will be greater than 0. Okay. So I output this as 1. Okay. So when I do the soft decoding, I'm adding the value. So you can turn so that the LLR values in this particular case are proportional, directly proportional to the whatever you receive for BPSK. Okay, so you can just add those values and see if it's greater than 0 or less than 0. Now you're correctly decoding as 1. Okay, you understood the difference between these two. Okay, so here effectively you're taking into consideration the confidence level that you have on this particular bit. Minus 0.1, most probably it can be as 1. That's what you think. So you're taking the confidence level into picture when you're doing this soft decoding. Okay. So now all the receivers are soft decoding receivers. No one uses hard decoding anymore. Okay. Effectively, soft decoding, in even the worst case, it gives you a 3 dB gain over hard decoding. Okay. Why was I telling you this reason? This because of this slide. Did you understand this hard decoding and soft decoding? Okay. Just remember this concept. I mean, that's all you have to do. So at the receiver, what they do is the punctured bits LLRs are set to 0. What is meant by LLR set to 0? LLR set to 0. Remember, LLR was what? Logarithm of probability of 1 divided by probability of 0. If this is equal to 0, it means the input you are equally confused. Whether it's half or whether it's 0 bit or 1 bit. Okay, so you set it to 0. The punctured bits are set to 0. The shortened bits LLR is set to the corresponding to bit 0. Okay, which is minus infinity or which is a larger number here. Okay, that's what I wanted to tell you. So now look at this slide with this thing in mind, and then it will make sense. Okay. Any questions? Okay. Okay. So next class onwards, I'm going to teach you a little bit about layer mapping and MIMO. Okay. So next 2 classes will focus on MIMO and whatever, what is meant by port, what is meant by definition of port, how do you do layer mapping, other things. So there's only one more block in the bit something of the bit interleaving. I'll do that in the next class, and then we can go into layer mapping and MIMO. Okay. Any other questions? Okay. If not, we'll stop. So I would suggest you to please look at the slides once. I have already uploaded that. I have uploaded in the normal stream. Please look at the slides and ask me any questions if you have. Okay.
One request.
Sir,
that assignment 2, sir, I request Milind to take one class, sir, for the solution code this coming Monday, sir, if it's possible.
For the MATLAB.
Yes. So that's
sure. I'll ask Milind to take
yes,
it. Okay. So by the way, were you able to do the theory assignment? Theory assignment was very straightforward. I mean,
yes, sir. That is
coming
Monday.
And upload it by Monday so that I can give the next set of homework for that.
Yeah. So one of the assignment is blank, sir. You have assigned, but no deadline and no details are available.
Something wrong. I mean, that's not an assignment. I mean, just which is this assignment? I can't.
LDCP, sir.
I think that is the class number. Just to add, sir has added that.
Oh, that's only lectures. I just add the class number so that this is the videos by Professor Andrew, na?
Yeah, it is showing as view assignment.
I'll put this as assignment. Okay.
Yeah, sir.
For some weird reason, this is showing as. Okay, I understood that. That's what I was wondering. Yeah, I know. I will remove this. I'll remove this and properly put this. Sorry. Okay, that's not an assignment. There's nothing there in that. The only assignment is homework 3, the TDD, SIP and patch. Please finish that, and what we'll do is Monday I will give you other assignment. Okay.
Perfect. Thank you.
Sounds good. Thanks everyone.